Welcome to the world of engineering drawings, a universal language for engineers, designers, and manufacturers. These drawings ensure every part of a machine is described with precision, leaving no room for error. Unclear drawings can lead to malfunctioning or unsafe products. Mastering clear, accurate drawings is essential in engineering. This guide focuses on flexible components, springs, belts, and chains, which require special drawing conventions. Unlike rigid parts, flexible components bend, stretch, and move, demanding unique symbols and rules. A good drawing shows not just the appearance, but also the function and placement of these parts in an assembly. For flexible components, visual clarity is even more critical. Drafters must show paths, tension, and link counts to ensure correct assembly and maintenance. Clear representation prevents costly errors and ensures proper machine operation. In the following sections, we'll cover standard methods for drawing springs, belts, and chains. You'll learn both schematic and detailed views using industry conventions. By the end, you'll be ready to represent these parts confidently and professionally. Flexible components are machine parts designed to bend, stretch, twist, or compress. Unlike rigid parts that hold their shape, they enable machines to absorb shock, transmit power, and control motion dynamically. Springs store and release energy, providing cushioning and controlled force in countless applications. Belts link rotating shafts, transmitting power efficiently. Think of a car's fan belt. Chains, made of connected metal links, transfer power without slipping, like a bicycle chain. Each type has unique strengths: springs for energy storage, belts for quiet power transfer, chains for high torque and precise timing. Without these components, many machines would not function. Springs, belts, and chains add flexibility and dynamic function to mechanical systems. Their movement and force transmission make them essential in everything from vehicles to industrial equipment. Understanding their roles is key to drawing them accurately. Let's explore how to represent each type in your engineering drawings. When drawing springs, clarity is key. Don't draw every coil. Use schematic symbols, a rectangle with a diagonal line, or a zigzag pattern to indicate a spring's presence. For more detail, outline the spring as a rectangle and use phantom lines, long dash, two short dashes, to show coils. Another method, draw a few coils at each end, connected by parallel center lines, to suggest a helical spring. Always focus on communicating function, not photorealism. Pair the symbol with a note or bill of materials reference. Drawings alone don't specify everything. Include specs like free length, wire diameter, number of coils, material, and spring rate in your notes. The drawing shows where the spring goes. The notes tell what kind to use. This separation keeps your drawing clean and readable. Mastering these conventions ensures your intent is clear to manufacturers. Different springs require different conventions. Compression springs are shown simply. Extension springs need hooks or loops at each end for attachment. Torsion springs are drawn with their coiled body and extended legs, showing the angle for force application. In sectional views, don't hatch the coils. Show the spring in full to avoid confusion. This exception to sectioning rules keeps drawings clear. Less common springs, like Belleville washers or garter springs, have their own standard symbols, usually simple shapes with notes. Always use the simplest, most recognized representation. Provide all manufacturing details in notes or tables, not in the drawing itself. Your goal guide the manufacturer, not overwhelm with detail. Consistent, standard symbols make your drawings easy to interpret. Simplicity and clarity are your best tools. For belts and pulleys, schematic representation is essential. Draw pulleys as circles, face view, or rectangles, side view, accurately placed for correct center-to-center distance. Show the belt's path as a continuous loop using phantom or thin solid lines. No need to draw teeth or cross sections. For two pulleys, connect tangent points with straight lines and wrap arcs around the pulleys. Indicate direction of motion with arrows along the belt path. For complex systems, clearly show the entire belt route, including idlers. Specify belt type, length, and part number in notes. Do the same for pulley details. Keep the drawing simple, with technical details in a bill of materials. This approach ensures the drawing is both readable and fully informative. Schematic clarity and precise notes are key. Drawing chains and sprockets is similar to belts and pulleys. Focus on the power transmission path. Sprockets are shown as circles. Use phantom lines for the pitch circle and thin lines for the outside diameter. Represent the chain path with a phantom line following the center line as it wraps around sprockets. This chain line shows the route without cluttering the drawing with individual links. Chains require a note specifying type, pitch, and number of links, critical for correct assembly. Different chains, roller, silent, engineering class, look similar in drawings. The note distinguishes them. For example, roller chain, ANSI number 40, 120 pitches. The symbol shows where the chain goes. The note tells what to use. Always prioritize clarity and completeness in your notes. Schematic lines plus precise callouts ensure the right part is used. This method keeps your drawings clean and functional. Professional drawings rely on clarity, organization, and adherence to standards. Use industry standard symbols, ASME, ISO, for springs, belts, and chains. Avoid unnecessary detail. Schematic symbols keep drawings readable. Place detailed specs in notes or a parts list, separate from the graphic representation. Keep your drawing space organized. Use concise language in notes. Position notes close to features, using leaders to point directly at components. Include all critical info size, material, length, part number, and installation instructions. Consistency is vital. Use the same symbols, line weights, and text styles throughout your project. A consistent approach reduces errors and looks professional. Think about how your drawing fits into the larger project. Clear, standardized drawings are the mark of a skilled drafter. Modern engineering drawings are created with CAD software, offering powerful tools for flexible components. Use blocks or library parts for springs, belts, and chains. Insert them quickly and maintain consistency. CAD lets you attach detailed specs directly to components, linking symbols to database entries for wire diameter, material, and more. Parametric modeling ensures the bill of materials matches the drawing, reducing errors. 3D CAD allows you to model actual geometry for design checks and motion simulations. For manufacturing drawings, switch to simplified 2D symbols with a few clicks. Set line styles for chain and belt paths automatically, saving time. Focus on design, not repetitive drafting. Mastering CAD features is essential for today's engineers and drafters. Efficient CAD use leads to clearer, more accurate drawings. We've covered essential methods for representing flexible components in engineering drawings. The goal: clear communication using standardized, simplified symbols. Don't overload drawings with detail. Use schematic views and place specs in notes or a bill of materials. Practice drawing assemblies with springs, belts, and chains to build confidence. Study professional examples and industry standards like ASME Y14. Consistent, clear notes and symbols make your drawings easy to read and manufacture. Your ability to create clear drawings reflects your skill as a designer. Think about how to communicate your design, not just how to create it. Mastering these conventions is a key step toward professional engineering. Keep practicing, focus on clarity, and your drawings will stand out. You're on your way to producing professional, effective engineering drawings.